specifically to address
Yes.
the issues with lattice parameters.
Yes.
Can you, in the context of what you just said in response to Ina's question, can you talk a little bit about lattice parameters?
Yeah, no, well, that's critical too. I mean, in fact, I didn't really mention it here or even in the paper I drafted, but I should. The ferroelectric phase, of course, is denser because it's the high pressure phase, ultimately at 100 GPa. But at these lower pressures, that's not necessarily so. So getting the delta V of the different phases is critical here. And it's pretty small number, the delta V between one of these phases and another. So it's basically whether you're condensing out one zone boundary mode or a different zone boundary mode or just a zone center mode. And if you do the same calculations, it's fixed volume. It's not, of course, ultimately with thermodynamics, things have to agree, but it's not so obvious, until you really do the full equations of state and get the enthalpies right and all of that. The exchange correlation potential matters too, yes. And I did not do like a exhaustive test of like different exchange correlation potentials.
Depending on even using common exchange correlations, you can get truly terrible lattice parameters. Like type V.
Yeah. Yes.
I think we've got to start figuring out what to do about that.
Yeah. What we need some exact on the fly exchange correlation potentials. Yeah. Okay, I'm going to turn it over to the chair. And there's 2 clips and 2 bottom parts. You have places to clip. So if you can clip those 2 on.
Both of them? What about this one?
Any pocket. Oh, you need to clip on both of these.
Oh, okay. Yeah, thank you.
Is that okay? Oh, let me make sure we're recording, right? Yeah. You checked it? Yes.
Good morning, everyone. Can you hear me clearly? Yes, great. Thank you for the introduction. And my name is Bo. I'm currently a postdoc from Livermore National Lab. And first, I would like to thank the organizer for having me here and giving me the chance to present my work. My topic today is on the strain phase equilibrium and strain phase diagram of ferroelectric materials. And it's my work, collaboration work with my previous PhD advisor, Professor Chen at Penn State University. And essentially, we're proposing a simple, universal, and efficient method to construct the strain phase diagrams for ferroelectric materials. As we know, the mechanical strain can play a huge impact on the ferroelectric material properties. And actually, the community of ferroelectrics, we have playing around with the strain engineering game for more than 2 decades. The early work, which I highlighted 2 of them here, is one is the idea is to increase the Curie temperature and the ferroelectric property in barium titanate when grow it on a substrate by the strain engineering. And another one is to make the room temperature incipient ferroelectric to be STO to be ferroelectric, also using the misfit strings. And recent years, there's a growing interest in fabricating these freestanding ferroelectric membranes, which is substrate-free and which allows you to apply huge mechanical deformation and as well as more complex strain state to these materials. Which means I would like to quote one remark from this editorial paper from Professor Julie at MIT, where he said that we can rationally engineer the 6-dimensional elastic string, which is a continuously tunable set of variables, just like we can do with the chemical composition of a septenary alloy. So which means there's plenty of room in the string space that we can explore to activate more unprecedented properties in ferroelectric materials. So there are a few existing theoretical tools if we want to calculate a string phase diagram of ferroelectric materials. Some of them, they are based on some a priori assumption on the domain structures, while some of them, they do not need this assumption, but requires extensive numerical calculation. Let's take the lead titanate 001 oriented thin films as one example and see how this different method perform. So with the monodomain model, they can predict the phase diagram like this for lead titanate. However, as we know, the rhombohedral or AA phase in lead titanate thin film has never been really observed in experiments. Otherwise, they can also assume some simple domain structures and also based on the Landau theory to predict phase diagrams. And this one gives a reasonably agreement with experiments, especially for the ferroelectric phase transition temperature, but they are slightly off when predicting the ferroelectric transitions at low temperature. And one of the state-of-the-art is using the phase field simulation to explore this string and temperature space, and which can give you qualitatively well match with the experiments, which is impressive. But if we really want to explore the high-dimensional string space, that is too much computational expensive. So we want to propose a simple method to help construct these high-dimensional string phase diagrams, and without the a priori assumptions. So to achieve this, we take a step back and review what we have learned from textbook of the thermodynamics of materials. And in the class, we have been told that for a binary system, if we know the Gibbs free energy of the two components as a function of temperature and composition, we can construct this like a eutectic phase diagram for the binary system. And we do not need to make any assumption on the microstructure between the alpha and the two beta phases. So can we do the same with the string phase diagram? So our initial attempts has been made by my previous colleagues, and their attempt was based on a few observations. First, the strain and stress are thermodynamic conjugate pairs, just as the composition and the chemical potentials. And also the chemical equilibrium condition, which is a uniform of chemical potential within the system, can be draw analogy with the uniform of stress component. And the multi-phase regions in the chemical phase diagram is determined by the lever rule, which is a common tangent between these two Gibbs free energy of the two phases. And likewise, we can also make use of the common tangent construction to determine where it should be the two-phase regions. And what's more, using the levers rule, we can quantitatively estimate the volume fraction or phase fraction of the different phases in these two-phase regions. And recently, we found another critical observation for this analogy, which is that the strain phase diagram and the stress phase diagram actually has a very close relationship. I will skip these equations, but the essential idea is if you start with the Helmholtz free energy as a function of strain, and to predict the two-phase regions, you need to find the common tangent between the energy surfaces. But if you start from the Gibbs free energy in terms of stress, you just need to find the crossing point of the Gibbs free energy surfaces, which is a lot of easier than finding the common tangent, especially for high dimensional strain space. And by using this 1D model, by intuition, we can generalize it to 2D, in which case there are 3 phases coexisting and a triple point in the stress phase diagram constructed by the Gibbs free energy surfaces. While for the Helmholtz free energy in terms of the strain, we can have this triangular region, which represents the 3-phase region in the strain phase diagrams. We can even generalize it to higher dimension, although it's a little bit challenging to visualize higher dimensional free energy surfaces. But the phase diagrams, we can, by intuition, we can get some notion how it would like topologically. And here's a more simpler representation of the phase diagrams for 1D strain, 2D strain, and 3D strains. I'll just give one example. Like in the 1D case, for the strain phase diagram, the 2-phase region is actually a segment, but in the stress phase diagram, it's just a point, like 2-phase point. And similarly, in the 2D strain state, it's a triple point of 3-phase coexistence, corresponding to a triangular region in the strain phase diagram. And for the 3D, it becomes a tetrahedral 4-phase region. And we can generalize this Gibbs phase rule, the levers rule, and the common tangent constructions from 1D to 6D strain space. With the Gibbs phase rule, it tells us in each phase region, what's the maximum number of phases can exist in that region. And with the common tangent and the lever rule, give us a quantitative estimation for a given total strain state. What are the volume fraction for different local strain phases? And this is all good, but they're all just intuition and schematics. We apply this theory, which we call strain phase equilibrium, to some real materials. First case is the lead titanate, and we consider the tetragonal phase, which has 3 domain variants in the 001 orientation. And the input we need is just like a mono-domain lambda model from the early paper, and the coefficients also from the lambda free energy 6th-order expansion. So we can construct this strain phase diagram and stress phase diagram for given temperature of the 001 oriented lead titanate. And what's more interesting is that due to the dual relationship which I showed between the strain and the stress phase diagrams, there's a nicely correspondence between this strain and stress phase diagram just by performing the Legendre transformation, which means if you know the strain phase diagram, you can construct the stress phase diagram and vice versa. And we then do a sweep of the temperature, and which allows us to construct this 3D temperature strain and temperature stress phase diagram of the lead titanate 001 oriented. And because of the simple model, we assume it's actually quite fast. It's just take a few seconds, and I suppose that's due to the visualization of these phase diagrams, not the calculation part. It's actually all of the phase boundaries, phase regions, we can obtain the fully analytical expression for them. And we further take a 2D section across the diagonal line, which gives us the equal biaxial strained phase diagram, which is already calculated by other method. And we compared with the phase field simulations. We found 2 interesting points. First, at the high temperature, there's a coexisting between the paraelectric and ferroelectric phases, which was not predicted by any other method. And we found in literature, actually, this type of this finding is kind of controversial. And from these 2 papers, we have learned that, in short, the idea is so when there are 2 phase coexistence at high temperature, which means it's a 1st-order phase transition, but the previous theory predict it's a second order because they assume it's a monodomain, and based on the monodomain Landau type theory, they predict it to be a second order. But if we release that assumption, it could be a first order, so there will be coexistence of the paraelectric and ferroelectric phases. And another finding is that there's a large deviation from the phase field simulation for the phase boundaries. And to improve this, we can actually incorporate another term, interaction term between the coexisting phases to account for this coherent strain effect. But I won't go into details in today's presentation. Okay, we also applied it to a second example, which is the PZT. And for simplicity, we just consider a 1D strain case, and with the we just consider rhombohedral and tetragonal phase without considering the antiferroelectric phase on the rhombohedral side, so the PZO side. But with this simple model, we can also obtain the analytical expression for all of the phase boundaries. And we can identify like the critical lines, which the first order becomes second order, and also the triple points, which there are three phase coexistence. And when they two merge, they give us the tri-critical point. And there are a lot of details here, and I also would skip that. And to show the most interesting work, I think recently we have this strong interest in hafnium zirconate. And we found with a very simple model, we can predict the phase diagram of hafnium zirconate. Again, we're starting with a very simple model, only considering the bulk free energy, like the total free energy at 0K, and as a function temperature, and also the elastic energy term. In addition, there's a surface energy term, which scales with inversely with the film thickness. And all of the parameters can be found from the ab initio calculation in the literature. And with this simple model and the common tangent construction, we can obtain the temperature misfit strain phase diagram for hafnium zirconate systems. And as well, we can obtain the thickness versus misfit strain phase diagrams. And we have some qualitative observation, like the first thing is like the slightly tensile strain or slightly compressive strain can favor this orthorhombic, the ferroelectric phase. And also at a very thin film thickness, the cubic phase will be dominant because of the small surface energy of the cubic high symmetric cubic phases comparing to the other low symmetry phases. And there are some interesting observation of the topology for these phase diagrams, such as the critical point, which is kind of akin to this chemical phase separation. And also this eutectic-like shape is also reminiscent of the chemical phase diagrams for the eutectic binary systems. And I want to highlight one implication is that from the chemical phase diagram, we know the microstructure in this two-phase solution is depending on the position of the overall composition with respect to the eutectic point. And this gives us a new understanding for this strain phase diagram. We can understand the formation of domain structure as like eutectic domain structure when it's cooling down at this eutectic point in the strain phase diagram. Or if there's a deviation from that, it will generate the pro-eutectic domain structures where the microstructures are quite different from the eutectic point. And there are a few other applications or implications. For example, for the ab initio calculations, when you obtain this total free energy as a function of the misfit strain, you may want to do a step further to construct the common tangent, which may give you the two-phase regions purely based on ab initio calculations. And for the numerical simulation, such as phase field simulations, our method, although it's not very accurate predicting the domain boundary, but it gives you a hint, like a upper bound or lower bound, that how to select and speed up your simulation by performing some less simulation around these phase boundaries predicted by the strain by our approach. And what's more, I think because we are drawing an analogy with the chemical phase diagram, the Kalfa method has been well established, and there are many tools and notions in constructing the chemical phase diagrams. And we can really make use of those tools to help us establish the strain phase diagrams. Okay, with that, I would like to echo back these remarks from Professor Lee. And I hope my talk can make you believe to some extent that there's a strong analogy between chemical phase equilibrium and the strain phase equilibrium. And we can utilize it for us to explore the high dimensional strain space for ferroelectrics. Thank you.
Any more questions? This is nice of MK for mine here. And we tried shear strain.
Shear strain.
I mean, you see, you